Okay, we are continuing our video series on thermodynamics from our Physics 1 class. And what we have here is a chart or table that summarizes the processes we've introduced so far. And so it perhaps as I've been going through it realized this may not make a lot of sense to you right now in the absence of context. But we've essentially just introduced some terminology. Isothermal, meaning the same temperature. So the temperature is constant in an isothermal reaction or process. Isobaric, iso same, baric meaning pressure, like a barometer measures pressure. So in that case, P is constant, it does not change. We have isovolumetric, where the volume doesn't change. And we introduce this term adiabatic. What does that mean? It means that there is no flow into or out of the system. It's entirely self-contained. So if we apply that to the first law of thermodynamics, where the total change in energy in the system is equal to heat flow in minus work out, then what do these types of processes mean within that context? Let's try to make a little bit more sense out of this. Well, first of all, if we have isothermal, that means the change in temperature is zero. Okay, if the change in temperature is zero, temperature is a measure of how much energy you have in a system. So if the change in temperature is zero, then the change in total energy is zero. And so in order for that to happen, Q and W must be equal. Q minus W would equal zero. Or another way of saying that is Q equals W. So in an isothermal reaction or process, the heat in equals the work out, exactly. In an isobaric system, if the pressure doesn't change, what does that mean? Well, the heat flow in equals the change in energy plus work. So this is basically just that first law of thermodynamics rewritten. Instead of delta U equals Q minus W, if we solve that for Q, then Q is going to equal delta U plus W. So if we look at the first law of thermodynamics from that point of view, then the work done, we said before, was P delta V. So we'll just kind of tuck this away for now, kind of make a note of this. Again, this is something that will perhaps be more useful later on, but for an isobaric system, Q equals delta U plus P delta V. Let's look at isovolumetric. What happens when we have isovolumetric? The volume isn't changing. As we said before when we looked at this previous slide here, if the volume doesn't change, the piston's not going up or down, then there's no work being done because there's no d, there's no distance that it moves. So in an isovolumetric system, work is zero. So if we look at our first law of thermodynamics here, delta U equals Q minus W. If W is zero, then delta U equals Q. The W just kind of goes away, and so we've got Q equals delta U. All right, we'll kind of tuck that away in the memory banks. And then finally, adiabatic means that there's no flow going in or out. So we've got a closed system. There's no Q going in. There's no Q going out. All of the energy is self-contained. And so that makes this part of the equation become zero. So if we've got delta U equals Q minus W, and Q is zero, then it means that delta U equals negative W. So the total change in energy in the system is equal to negative work. Okay, so again, we're kind of building up to to the Carnot cycle here. So it may not make a whole lot of sense, but we're getting there. Okay, we can look though at an example problem applying some of these concepts right now before we get to Carnot. So we have this engine, and inside the engine we have gas. We have 0.25 mole of an ideal monatomic gas. So that just means that we've got a whole bunch of gas molecules in here. How many molecules do we have? 0.25 moles of them. Okay? And then it's going to expand rapidly. It's going to expand rapidly and adiabatically. So we're not going to get all of that heat energy is going to stay in the system. It's going to push against the piston and push it out some distance. It's going to move some distance, which means it's going to do some work. And in this process, the temperature of the gas is going to drop. So when you're going from high pressure to low pressure, temperature drops. And in this case, we're dropping from a very high initial temperature of 1150 Kelvin, and we're going to drop all the way down to 400 Kelvin. How much work does the gas do? So there's my animation. The piston gets pushed out, and the gas goes from hot to cold. Okay, so the problem statement said it was adiabatic. So that means that heat flow is 0. There's no Q going in, none of that, and there's no Q going out. All of the Q, all of the heat energy stays inside the system. And so from our previous slide here, we saw that if it's adiabatic, what does that mean? It means delta U equals negative W. Okay, so let's write that down. Delta U equals negative W. So basically what we're saying is the work that is done by pushing this cylinder is equal to the total change in energy. There's no heat left the system, so we don't have any kind of a byproduct escaping our system. It's completely self-contained, and all of that energy that was not created but transformed in this process was used to do work. Okay, and we have to go back to chapter 14 to get this equation for the energy of an ideal gas. U is 3 halves nRT. Okay, and so we've got 3 halves. N is the number of moles of gas, which was given to us in the problem statement. 0.25 mole. That's how many gas particles or gas molecules we have in here. 0.25 mole. And R is the constant, the ideal gas constant, and that is 8.314 joules per mole Kelvin. And then our temperature change, delta T, was given in the problem statement as going from 1150 to 400. So we're going to end up at 400 minus where we started, 1150. Okay, so our U, or delta U in this case, is going to be equal to negative 2300 joules. That's how much energy we had, and so that's how much work is being done. Actually, the work is just equal to the negative of that, so it would be positive 2300 joules worth of work. And work and energy have the same units because energy is the ability to do work. So how much work can we do with this much energy? 2300 joules. So we had, when we had this hot compressed gas, we had 2,300 joules worth of energy stored up in this system, and then we used it to do 2,300 joules worth of work. And let's see that animation one more time. Okay, let's move on to the second law of thermodynamics. The second law of thermodynamics basically says that there are some processes that can only go in one direction. So the image here that the textbook has is this broken coffee cup on the floor. Now, if we're looking at this in the opposite direction, why is it not letting me draw? What's wrong with my pen tool? There we go. It's just a little slow to show up. All right, so if we look at it going in this right to left direction, I'm having some technical difficulties here. There we go. All right, can you imagine a situation where a coffee cup gets knocked off of a table, falls to the ground, and breaks? Of course you can. You may have actually even done it yourself. Can you imagine a situation in which we have shards of a piece of coffee cup lying on the floor, suddenly they fly together, hop up into the air, and land on a desk? Does it make any sense at all for the system to go in this direction? No, of course not. So basically what the second law of thermodynamics is saying is that there are some processes that only go in one direction. You can't undo them. You can't unring the bell, as the expression says. So heat can flow spontaneously from a hot object to a cold object, but it will not flow spontaneously from a cold object to a hot object. So it's not reversible. You can't undo it. Hot goes to cold, and it will not go back in the other direction, no matter how much you want it to. All right, if we move on to the next section, we're going to start talking about heat engines. And I know we've still got some of those loose ends from earlier on. Like I said, we'll kind of tie those all back together when we get to a Carnot engine, which is a type of heat engine. So let's first introduce what a heat engine is. A heat engine is some type of mechanical device, typically, in which we input something at high temperature. So if you're talking about an automobile, we're igniting gasoline, which causes heat. Okay, that heat then goes into the engine. Some of it is used to do work, to actually make the car go. Okay, that is work. But not all of it goes to work. Some of it leaves the system at a lower temperature. And that is basically the exhaust gas coming out the tailpipe, if you want to think of an automobile. So we put heat in. Some of it's used to do work. Some of it is comes out the tailpipe and is essentially not used to do work. You know, there's our Thomas making another appearance. He likes to be useful and do work.